Hello, my name is Kyle Atkins Weltman, and I'm here to present the results of my work on math properties of end Cretaceous dinosaurs. So specifically, we're looking at this period because it's a very well-sampled and well-studied extinct ecosystem dominated by non-avian dinosaurs, some of which are very famous, like three-horned Triceratops and, the big famous Tyrannosaurus Rex. But we want to understand how these communities were structured and how these animals interacted with each other. Mass properties are a really good way to get at part of that. Specifically here, we wanted to look at turning ability, i.e. rotational inertia. To explain that, the higher rotational inertia you have, the more resistant your body is to changing direction. So the higher it is, the less agile you tend to be. And so we wanted to get this for not just a single animal, but for a variety of animals that lived alongside each other to make comparisons. So we made life models of 10 different taxa from this time period and environment, and we sculpted those life restorations using digitized skeletons where available, such as here, and where not, we used skeletal diagrams and images from mounted specimens. We also accounted for the air sacs and just respiratory spaces in general by sculpting those using osteological correlates and information from modern animals, and subtracted those from our models so that when we put them into Mesh Lab and computed volume, we were not counting those negative spaces. Then once we did that, we got estimated volume and rotational inertia for whole body for an animal turning while its feet are planted, and for axial body if an animal is trying to turn while it's, say, moving forward or backward. We used a lower bound of 800 kilos per cubic meter and an upper bound of 1,000 kilos per cubic meter for density for our mass estimation. Now, what we found is that there were 4 bins of body mass and rotational inertia ranges, as you can see here. But what's interesting is this particular one here, the body mass between 1,000 and 5,000 kilos, there are no adult animals from this area that fill that category or are even in that category. It's exclusively subadults of these 3 large taxa, T-Rex, Triceratops, and Edmontosaurus. And when you look at those, you see that Triceratops actually has a lower rotational inertia than T-Rex, even when it's bigger than T-Rex. Whereas Edmontosaurus that's bigger than T-Rex has a higher rotational inertia, and when you scale them to a very, very, very close to each other in size, they tend to converge. This hints at different predation strategies by T-Rex on these 2 taxa and different predation avoidance strategies on behalf of these 2 taxa when faced with T-Rex. Furthermore, because T-Rex is so drastically different when it's a juvenile compared to its adult phase, we decided to incorporate other earlier data that's been taken on rotational inertia of juvenile T-Rex. And when we do that, as seen here, this animal compares most favorably to these medium-sized dinosaurs in terms of rotational inertia. You've got your medium-sized Struthiomimus and your Pachycephalosaurus, your Dakotaraptor. And so this is possibly indicative of different prey preferences, which would avoid competition with the much bigger adults. That would potentially be a threat if they were trying to compete. So, in summary, the largest adult dinosaurs in our sample all fall within their own bin, and this may indicate an ecological class where these animals are interacting more with each other than they are with other smaller dinosaurs from other ecosystems. Then, in the future, we hope to use these mass properties along with estimates of the various musculoskeletal relevant parameters so that we can look at things like angular and linear acceleration, and to look at extant animals and ecosystems so we can test parameters that are going to be important for inferred predation strategies. So there's a lot to go, but we still have some very interesting preliminary research.